So our first talk this morning is going to be given by Browne. I believe the first author is also online, but not actually in the UK currently. Dan can fill us in on that. Anyway, Dan is going to tell us all about how to compile two local qubit Hamiltonians for quantum simulation. Just make sure you're mic'd up.
Okay.
The slides are coming up. And over to you.
Lovely. Good morning, everybody. Let me just check. Yeah. Start again. Good morning, everybody. So thanks very much to the organisers for putting this event on. It's been a superb event so far, and it's really great that you've managed to make this a hybrid online event as well, which means that my co-author, Lingling Lao, who is currently in China, is also able to attend, and maybe if Zoom works, she'll also be able to help me answer some of your questions at the end of the talk. I'm going to tell you about Toucan. That's a Toucan, if you're wondering, which is a compiler we've developed for a specific application on quantum computers. So Toucan sort of stands for a hardware-adapted quantum compiler for two local Hamiltonian simulation on NISQ devices. We took a little bit of license with the ordering, and that's, in a sense, that's a sort of an analogy for the way Toucan works, which we'll see in a moment. So we're thinking about a very simple Hamiltonian simulation problem where we're given a Hamiltonian and we would like to simulate the solution of the Schrödinger equation under the Hamiltonian. So we want to realize this time evolution operator, which is just the exponentiated form of the Hamiltonian. And a very common approach to realize this on a quantum computer is to use a Trotter approximated form, a product formula such as the one at the bottom, where we take our Hamiltonian, we split it into a convenient basis, for example, the Pauli operators, which we've done on the right, and then you can exponentiate each of these Pauli operators individually and form the product at the bottom, V of t. And V of t is an approximation of U of t, and in particular, in the limit that the time is made very small, it becomes a good approximation. And the important feature of this is that the order of the terms in this is arbitrary. One is as good as another. Okay? It doesn't make a huge difference on how well we match the exact evolution operator U of t. And that's one of the things which Toucan is going to use in designing circuits to implement these kind of evolutions on a quantum computer. So what do quantum compilers do? We already had a talk yesterday about quantum compiling. Roughly speaking, what a compiler should do is automate the process of taking your quantum problem and expressing it in a form that is realizable on a quantum computer, specifically a series of instructions that you would then send to your machine. And so, that's quite a vague definition. So there are many different types of compilers that take maybe quite a very high level description of the problem, such as a description of a molecule, a compiler which maybe it takes a description of a unitary matrix or of a Hamiltonian, and often at the moment, our compiler would take as its input some quantum circuit that we've written down without really thinking too hard about the constraints of the device. So, for example, we may write down a quantum circuit with 2 qubit gates, which are not present on the device, or indeed with gates that the device can't access. So what compilers should do is take this high-level description and convert it into the instructions which are going to be sent to the quantum computer. Now, at the moment, in many experiments, compiling is sort of done by hand. So here's a recent, very beautiful experiment by the Google group of precisely of a trotterized quantum simulation. And they're simulating the Fermi-Hubbard Hamiltonian, which you can see in the top right there. And essentially to do this, they compiled this by hand. So they sort of thought about their chip, thought about what their chip could do. So on the left is sort of a picture of the connectivity of their chip. The edges correspond to the. Is there a laser pointer? Okay, it's just a little bit weak, isn't it? Okay, it sort of works. So you see the edges, they correspond to the presence of 2 qubit gates on the device. And what they've done is, to solve this problem first, they had to identify how to represent the problem on their quantum computer. They had to make a matching between the logical qubits and the physical qubits on the device, which is numbering here. And then they figured out how to insert the quantum gates in sort of the best way to achieve the computation. And in doing this, they would have been optimizing to, for example, try and reduce the number of gates they use. Maybe they're trying to reduce the depth of the circuit to reduce noise. They may also incorporate some optimizations, particularly on an experiment like this, where they've used a small corner of a larger chip. They've maybe sought out the corner of the chip where the gate fidelities are higher and the noise rates are lower. So these are the sorts of optimizations which people do by hand and which compilers would like to automate. And the reason we really need to automate is that as quantum computers scale, this quickly becomes an intractable problem. So that was the sort of the motivation for thinking about compiling. And with Toucan, we wanted to take a different approach to the general compilers, which are very successful and which you'll find online. So here are 2 prominent examples. There's a compiler built into Qiskit, and also one called TQET, which has been developed by Cambridge Quantum. And these general purpose compilers are very powerful. You can sort of throw any circuit at them. You can sort of feed them with any sort of hardware constraints to specify your device, and they will produce runnable circuits. And they have very, very many clever optimizations built into them. But there are some optimizations which, you as a sort of a practicing theorist in quantum computing would know to implement that this general compiler wouldn't know about. A good example being in the Trotter approximation, the arbitrary order of the terms. So what our compiler is going to do, which these general purpose quantum compilers can't do, is use that knowledge to do compilation steps which would be illegal in a general purpose quantum compiler, which is strictly preserving the rules it's been taught about the way we should respect non-commuting gates in quantum circuits. So I've talked a little bit about hardware constraints, and we've seen some of these pictures. I mean, at the moment, this is quite a rapidly changing field, and every few months we hear about a new exciting large-scale device. All of them have their own topologies, so the layouts with which 2 qubit gates are implemented, and all of them often have their own 2 qubit gates. So there's not yet really a canonical universal gate set which is used in experiments. And these 3 experiments from Google, IBM, and Rigetti all use a different entangling 2 qubit gate. And so, the compilers for those 3 types of gates might work very differently. And one would want the compiler to be able to gracefully and automatically use the best optimizations for the hardware in hand. So compilers are typically built out of several steps. Not always in the order depicted on this slide. So you have to make a variety of choices. One of them is called qubit mapping, which, as I mentioned already, is the initial decision you have to make. How are you going to assign your logical qubits to physical qubits on the device? And then there's the qubit routing problem. Once you've made that assignment, some of your 2 qubit gates will be available to you on the chip, and some of them won't be. So as we heard in Annie Ruder's talk yesterday, there are a variety of approaches to solving the routing problem, but a simple one, and one that we adopt, is just to use swap gates. So you can use swap gates to move your logical qubits around so that the qubits that you wish to apply a 2-qubit gate to are now adjacent. So that's the qubit routing problem. Then there's the problem of gate decomposition. So we've seen there's a wide variety of hardware native gates. The chances are the unitary circuit that is your input is not already decomposed into those gates. So you have to do a decomposition step to reduce it to those hardware operations. And finally, there's the question of scheduling. What order do you implement these operations, and when do you implement operations in parallel? So compilers do all of these things. They incorporate all sorts of optimizations along the way, trying to reduce things like logical depth and the overall number of gates. And they don't necessarily work in this sort of sequential way. You can see there's a potential tension between the mapping you choose and the routing you choose. And some compilers will sort of go back and forth between mapping and routing in deciding the optimal placement of qubits and gates. So let me tell you about how Toucan works and what it does. So its input circuits are going to be trotterized evolution operators from two local Hamiltonians. So we're restricting the general problem of Hamiltonian simulation to this special case of 2 local Hamiltonian. The reason we're doing that is by restricting the problem in this way, we gain more optimizations we can make. So in a sense, there's a trade-off between the assumptions you make about the problem and the more optimizations you can build in to the compiler. And you can see that this assumption will be quite powerful for us and quite useful for us. So our input to our compiler is going to be a circuit of 2-qubit gates, looking something like this. So all of the gates are in SU4. They could, in principle, be applied between any pair of qubits. And to introduce some of the graphical notation I'm going to use, I'm going to use these sort of empty controlled unitary looking gates to represent a 2-qubit Pauli gadget. Okay, so this will be our input circuit. It's a description of all of these e to the minus I h k t Pauli gadgets, which I'm going to implement between each of the pairs depicted in the circuit. And our output should be a description of instructions, for example, maybe an open chasm description of the quantum computation. So the structure of Toucan is as follows. We start with a mapping step, we follow to a routing a step, then there's an optimization that we do in the middle, then we do the scheduling, and then we do the gate decomposition at the end. And the steps that are sort of shaded in light brown, those are the steps where we use the freedom to reorder this trotter decomposition. So let me go through them one by one. So the qubit mapping algorithm we use is a very simple one. We are simply trying to put the qubits as close together on the device as they need to be to implement the gates we want to implement. So we can just write down a simple cost function. It's easier to just illustrate it. So we can just sort of count the distance between the qubits of a particular 2-qubit gate we want to implement. So for example, in this example in the middle, this is weight 5, because it's going between qubit 0 and qubit 5. And ideally, we want to consider all possible permutations of qubits and choose the mapping where the total sum of these values is minimized. Now, of course, that's not efficient to optimize over all permutations, but there are good heuristic solvers. And we're using one called taboo search, which is quite commonly used in these sorts of compilers. So the mapping process we use is a fairly standard one, but importantly, we're already sort of using the fact that we're going to reorder the gates because gate ordering does not come into this cost function at all. Okay, we're already thinking we don't care where these gates come temporarily, we just care about sort of the distance between the qubits. So then we have the qubit routing. So the algorithm is written here in our paper, but rather than letting you read that, I'll talk you through the basic idea. So what it does is it essentially tries to split the circuit up into particular slices. Each slice will correspond to a different qubit mapping. And in each slice, you try and implement those gates which are now nearest neighbor with respect to that mapping. So you start with your initial mapping that was computed in the last step. You work out what are all the nearest neighbor gates in that mapping. And those are the gates you implement first. And then you start to introduce swap gates to achieve other mappings. And we have a particular heuristic which picks the best swaps, essentially using a heuristic approach which sort of captures the intuition you would probably use if you yourself tried to decide how best to reorder these qubits. Once we have chosen where to put our swaps to make the next mapping, we identify all of the nearest neighbor gates with respect to that mapping, implement those, and then we move on to consider the gates in our input circuit which are not yet assigned. And again, we first identify the one of those which is easiest to implement, again, find a set of swap gates which will remap the qubits such that that gate becomes nearest neighbor, and then we repeat the process at each stage, bringing forward all of the gates. Once we've decided on a particular mapping, we bring forward all of the gates which would be implementable as nearest neighbor gates with that mapping. So here's a little example. This is what, for this particular gate on the left, so a generic compiler which needs to preserve the ordering of the gates would come up with something like the middle, and you see there are 3 separate mappings there that it has decided upon. Just to illustrate my, to explain the graphics here. So at the bottom we have a picture of, this is 6 qubits and they are arrayed in this 2x3 rectangular grid structure. And so the lines there represent the qubits that are nearest neighbor on the device. And you see these, inserting the swap gates, we move from one mapping to the next. And in this simple example, Toucan is able to achieve the circuit on the left with just 2 different mappings, where the generic compiler needs to use 3, because we've taken advantage of the ability to reorder our gates. Then we do a very simple trick, which is possible because we're only working with SU4 gates as our input. So all of the Pauli gadgets are 2 qubit, the swap gates are also 2 qubit. So it's convenient to merge them together into a single unitary. So we take the opportunity, whenever we have consecutive 2 qubit gates on the same pair of qubits, we merge them together into a single unitary. The reason we can do that is that we've not done the gate decomposition yet, so we don't need to try and protect any particular gates which may already be associated with a hardware instruction. We have the freedom to combine them together. And finally, there's the gate scheduling step. So again, this is the algorithm. I'll give you just a sort of an overview. I mean, essentially what this is doing is trying to reduce the circuit depth by implementing gates at the same time as much as possible. And we use the rule that at each layer, each qubit is allowed to be involved in only one gate operation. So this transforms into a graph coloring problem, which we can automate, and allows us to sort of maximize the number of simultaneous gates we can implement. So essentially, in each one of these mapping slices, the scheduling is done, this parallelization is done individually, but again, we have the freedom to move gadgets between cycles to reduce the depth where we can, and sort of by working backwards, starting with the end of the circuit and then coming back, then sort of moving backwards in time, we're sort of making the decisions in the opposite order to the way they were made in the first round, and that allows us to improve the depth further somewhat. So the final step, which is quite a powerful thing we can do. Because we're only working with SU4 gates, and because we haven't yet done a hardware decomposition, we can do the hardware decomposition at the end. So what that means is we take our circuit of SU4 gates, and each of these individual SU4 gates can then be decomposed into the hardware native gates. And that means that the compiler is essentially agnostic. You just plug in the gate decomposition algorithm you might need, for example, to go to Sycamore gates, or CNOT gates, or ISWAP gates. And we used third party, obviously, IBM provide one in Qiskit, which decomposed to their gate set. Google provide one in Circ, which decomposed to their gate set. And we also developed our own numerical routine if you had a really weird and unusual gate set, which wasn't amenable with analytic methods. So putting this all together, we have a compiler. And so we then tested it using a variety of example cases to benchmark it against the competition and to see how it performs compared to these general compilers. And the problems we chose to study were next nearest neighbor spin chains. So this would be chains of qubits which are coupled as indicated here in the diagram with these dashed lines indicating the next nearest neighbor coupling. And we also tested it with QAOA. I mean, QAOA has the same, QAOA circuits have the same form as Trotter circuits, so we can use the compiler here. I mean, in QAOA, the individual sort of Pauli gadgets that you apply together, they commute. So, you know, people already knew that you could reorder them, and there are other you could permute the order, and there are other QAOA specific compilers out there, which again, we could benchmark this against. And we tested it targeting a range of different hardware, the ones I've introduced already, both against the general compilers and these application-specific compilers. And the bottom line is it works extremely well. So here are some graphs of various figures of merit for the compiler. This is looking at next nearest neighbor spin chains on the top, so that the Heisenberg model at the top, and on the bottom for a particular QAOA example. And the thing to look at is, so there are a few variants of toucan which I haven't discussed, but these are the dark gray and dark blue peaks here. And we're looking at the number of 2-qubit gates here. We're looking at the depth, and we're looking at the number of swaps. And with respect to each of these metrics, the toucan is outperforming the general purpose compilers, which, you know, it should do because of all of the extra tricks I've just introduced to you, but it's reassuring that it actually does. And here again, some comparisons just with numbers. So each of these are just the factors with which toucan beats other compilers for a variety of metrics across the different architectures and across the different benchmarks. And here you see particularly strong advantages with the Sycamore and Aspen chips, where the 2-qubit gates are not CNOT gates. And most of these general purpose compilers are really designed to target CNOT plus single qubit architectures. So we see the advantage here that we can sort of target specifically our gate decompositions at the devices in question. We also tested it in an experiment. We looked at, we ran a QAOA experiment on an IBM chip. And the thing which is particularly nice about these results, so here we're comparing against some of the other bespoke QAOA compilers, and we outperformed them. And in particular, we compare the results from single layer QAOA with two layer QAOA, and we've sort of achieved the holy grail of QAOA, which is we actually improved performance by adding a layer, which is generally hard to do with NIST devices at the moment. So it's satisfying that we've achieved it. And in particular, the other compilers for this problem do not achieve that. So, you know, by taking advantage of these optimizations, we were able to use much smaller and lower depth circuits, which boosts the performance of the algorithm in practice. So to conclude, I've introduced to you the toucan compiler. It's really, so it's an application-specific compiler, which is taking advantage of two specific problems, no, two specific properties of the problem we want to compile. The fact that the gates can have an arbitrary ordering and we can re-permute them, and the fact that all of the input gates are SU4. There's a lot of future work we can do. It'd be interesting to sort of split these two properties apart and make compilers, for example, that focus on SU4-based circuits, which are quite common. This is sort of the language we often write quantum circuits down in. And also we would like to also look at more general Hamiltonian circuits with higher weight Pauli terms, such as, for example, the fermionic circuits that I illustrated with the Google example at the beginning. So thank you very much for listening. I'd just like to make two announcements at the end. So as of today, Toucan is open sourced. So Ling Ling has very kindly open sourced it ready for you to take a look at. So if you go to that URL there, you can have a look at our source code, and you can even install it with pip, which I'm very excited about. So the open sourcing has been supported by Unitary Fund, and most of the work was done funded by this EPSRC project, and we have postdoc positions available at the moment working on this kind of thing, and also more general topics related to quantum simulation with myself and my colleagues Toby Qubit and Luis Masanes. So come and talk to me if you're interested in that. But thanks very much for listening.
Fantastic, excellent talk, Dan. Do we have questions?
So, as far as I understand, you sort of assume the trotterization already happened.
Yes.
Right? So there are these techniques where you do this sort of randomized compiling with the trotterization, where
yes.
you mix it in a certain way and that reduces the error of things.
Yes.
Now you're sort of non-randomly ordering the terms.
Yeah.
Does that affect like how fast it converges to the right unitary at all?
So that's a very good question.
Can you repeat it just to
yes,
make sure that the online people get it?
So the question is, this one property of trotterized circuits which has been used to improve the convergence is the idea of randomizing the order. So there's a nice paper by Earl Campbell and co-authors on this, and also Andrew Charlton and co-authors. This is something we have thought about. So our compiler is not sort of randomizing the order in the sort of the in a sort of proper way, but nevertheless it is sort of generating an arbitrary order in some sense. So it is something we've considered whether this compiler could somehow also reduce the trotter approximation error in that same way. I mean, what you'd need is, so in those approaches, you're averaging over different realizations of the unitary. And so what we would need to do is add sort of a random component to the compiler. Now we haven't done that yet, but there are several points where that might be possible, and there will be a sort of trade-off between compiler performance and actually randomizing it according to the sort of distribution you would like to use. So that's certainly something we're interested in studying more in future work. I don't think we have any concrete results on it yet.
Do we have more questions? Yes.
Yeah. So you showed how your compiler outperforms other compilers, in terms of slot gates,
yes,
and so on. What about the classical time, like compiling time?
That's a good point. So I didn't mention that. So we didn't compare directly, but this is an efficient algorithm. So the main parts of the algorithm have a quadratic time complexity in the number of qubits. So it's a fast performing compiler, but we didn't directly benchmark it. It'd be interesting actually to check that. Actually, I don't know why we didn't do that, but I suspect it probably performs. Its performance is probably very competitive, and that's something we should look at. I don't know. So Ling Ling, are you there on the call? You might have something more to say on that.
Yeah, I'm here. So we didn't really benchmark every circuit for the speed up, but we have some numbers in the paper, like for compiling a 40 qubit circuit, the routing and scheduling just takes a few seconds. So it's quite fast. But also, so the runtime also depends on the implementation of the code. So I think the scaling of the algorithm itself means that it's scalable, it will be fast.
Thanks, Elaine.
Sorry, I don't know if you can hear me.
Yes, we can hear you very clearly. Could everyone hear? I could hear. Yes, we can hear you very clearly.
Okay, great.
Thank you.
Yeah, thank you.
Great. I think given the time, unless there's another burning question, we should move on to the next speaker. After, of course, thanking Dan.